Welcome everybody to the February 2025 meeting of the Mornington Peninsula Astronomical Society, and as usual we'll go through a few things before getting into the meeting proper. The first one shown at the top centre of the screen is a picture of Mike Dinn. Those who attended the March 2024 meeting here, we had a Zoom connection with him through Tidbinbilla. He was the director for Tidbinbilla for most of his career, or a deputy director, and also at Honeysuckle Creek. And he was awarded the Medal of the Order of Australia at Australia Day. So if you recognise the face, he was the one on the end of the Zoom connection when Stephen Slater was here giving his talk. And that was for services to engineering in deep space tracking and exploration of all the Apollo missions, all the Pioneer and Voyager, and also the Magellan and Galileo missions via the Tidbinbilla radio telescope and the one at Honeysuckle Creek. Over at the top right-hand side there is shown one of the two satellites that's part of the NBN network. So not everywhere in Australia has the wonderful NBN wired connections that we do have in the metropolitan area. And the parts that you can't easily get a bit of, dare I say, copper or optic fibre to, has to go via this satellite. Now, to give you an idea of the size of the satellite, look in the bottom right-hand corner of that picture, and you'll see the size of a person relative to that satellite. So they're pretty big, two of them that NBN runs. They're called Sky Muster satellites, and they're geostationary. So they're up in geostationary orbit, which means they're a long way from Earth, and they do one orbit of the Earth in exactly the time it takes the Earth to turn around once. So the gist of that is that if you look up in the sky at them, they'll just look like a star in the sky that's moving through the sky like any other star. So not like a Elon Musk SpaceX Starlink satellite. These ones stay. The only problem is NBN has come out and said that they're planning on changing that when those satellites reach the end of their life in the next few years. They intend going the Elon Musk route of putting up a constellation of low Earth orbit satellites to do the same thing instead. So Elon Musk, I think, has plans for 40,000 satellites as part of Starlink. At the moment, they're barely, well, I think not even a quarter of that are up there yet. So Australia will be doing its bit to add to the light pollution going overhead at that time as well, if they don't change their minds. Bottom left-hand side there, showing the International Space Station. The two astronauts that have been up there unexpectedly for a few extra months, Suni Williams and Butch Wilmore, are being rescued, in inverted commas, by the US President, who's bringing them back 2 weeks early. And by doing so, it was originally going to be a Boeing space vehicle that actually went up to bring them back, but it's now going to be a SpaceX vehicle that's going to go up to bring them back to rescue them 2 weeks before they otherwise would have come back. And the current literature in the spaceflight online media is that Artemis, which is the mission to go back to the moon and then onto Mars, may very well be the Boeing parts of it, which are going to be the Space Launch System vehicle, the one that we've seen launch before, may be replaced to be the SpaceX Starship instead. So a very, very significant move if that is the case. I wonder why, yes. So NASA has not actually confirmed any of that yet, but it's a case of, I think, leaking it out to manage expectations, and then things will change in time. Down in the bottom right-hand corner of the screen, if you've got eagle eye, you'll see a couple of dots moving by. This is asteroid 2024 YR4. This was the one that about a year ago was given a 1% chance of impacting Earth in 2032. It's now been increased to a 2.2% chance, so about a 1 in 45 chance of striking Earth on the 22nd of December 2032, so it could could ruin somebody's Christmas for sure if it hits. It's thought They're not entirely sure yet, but it's thought to be between 40 and 90 metres diameter. So it's roughly the size of the one that landed in Tunguska in Siberia in 1908, which was somewhere around about 50 to 60 metres diameter. And it would do about the same amount of damage if it actually struck Earth. So it's not going to wipe out life on the planet. It's probably not going to wipe out a country, but it would certainly wipe out a city if it struck. And they're looking very, very closely at it now and its orbit, and because these things can be a little bit chaotic as well. And so as the number of years count down to 2032, they'll have to kick in possibly with mitigation action to give it a bit of a nudge out of the way. So this one, although they're not ringing the alarm bells, they're sort of flagging that it's the most concerning one that they've had to date, and even talking about the possibility of evacuating large areas if necessary, once they accurately work out where it's going to come down. Well, you could be lucky, you could be very unlucky. Most likely it'll land in the ocean, given that most of the Earth is ocean. But even then, that would cause a bit of problem with tidal waves, I would think. All right, now for tonight, very unusual start to the meeting, but I'd ask you all to be upstanding for 1 minute silence for the passing of member Tony Nightingale recently. All right, thank you. And his service is tomorrow at Chelsea Heights at 11 o'clock. All right, now on to the meeting as usual. Welcome everybody to this month's meeting of the Mornington Peninsula Astronomical Society. I'll welcome the new members who have joined since the last meeting. We have Michael Barrow, Michael Sharp, Bruce Botton family, Jack Handley, Henry Prizdochkin, I've probably well and truly mangled that name, Second Satvir, Anish Deshmukh and family, and Pamela and Richard Kammerhofer, and Lena Smirelli. Welcome all of those. Any of the new members here tonight? Okay, if there are anyone that has joined fairly recently, our new members officer will now put her hand up in the air for you to see. Yeah, there it is at the back. And feel free to say hello to Nerida. All right, we'll look at what the Society's done in the past month and the upcoming month, and then I'll throw over to Chris to do the monthly photo challenge and Guido for Sky for the month. Then we'll show a video that was from Monash University of Professor Emeritus, which means he's retired, Kip Thorne from Caltech in the USA. One of the true greats of theoretical physics, up there with the likes of Stephen Hawking, who is no longer around, but Kip Thorne well and truly is. This talk tonight was given before gravitational waves were discovered, but only a couple of years before, and he ended up getting the Nobel Prize for it a couple of years after this, and he talks about that at the time, that the prediction that it would be very soon. Okay, so recent events here at the Briars. We had on 17th of January the last of the public nights for January, and we were packed with 123 visitors, and fortunately not very much cloud, so we were able to go outside. The talk was given by Guido. Then we had the working bee that Saturday at the Briars as usual. And committee meeting was the following week, where committee talked about leases and getting a snakebite kit, which we now have with the first aid kit in the kitchen, and stingos, and we bought some more almanacs. So if you're after the 2025 astronomy almanac, we do have a small number left, and also talked about running the speaker training again for those who would be interested at talking at schools and public nights and that sort of thing. 1st of February, the cosmology group met here on a Saturday, and they had 25 present, which was a good turnout. 7th of February, we had the February public night here at the Briars with 94 visitors, and fortunately again, very little cloud, and Guido stepped in to give that talk, with Trevor having to pull out at the last moment. Last Saturday we were here for indoors for the trivia night, and that's the picture you see in the background there, taken by Phil Peters. And we had 65 in the audience, and at least 2, if not 3, bursts of rain during the evening. And fortunately, it cleared up brilliantly for them to actually see outside after the concert. But it was a good call to actually have it indoors, which meant having to limit the number of tickets that we could sell. But it was a good call in the circumstance. Coming month, we've got a fair amount coming up. We've got this Saturday the Working Bee and a members barbecue at the Briars, starting at 4 o'clock. 23rd of February, which is this Sunday, we're going to be at the Bentley Street Festival. MPAS will have its 6x3 marquee there set up on Centre Road, and I imagine Trevor will send something out on East Scorpius in the next day or two for those wishing to attend. We'll be there all day long. It just means we have to get in early before they close off access to the road, and then you're locked in until they open up at the end of the day, the so-called bump in and bump out. Next week we have St Mary's College here at the Briars. They're staying next door at the camp, and we've got year 8s there, and Catherine and I will give that particular talk to them. Committee has been bumped to next to Friday, the 28th of February, and we'll do that by Zoom, I think. Then we have Parkdale Secondary, which we do once a year, and it's usually a very large group, up to 200 of their year 7s, and this will actually be held at the school as normal. And that date was changed. Originally they had it as 25th of March, but they pulled it forward when they realised that the moon wouldn't be visible on that date, so that's why the date had to change. Public stargazing night at the Briars on the 7th of March. We already booked out for that one, and Manfred will be giving the talk for that one. Then the following Monday, which is the Labour Day weekend Monday on the 10th of March, we've got the Somerville Family Fun Day, which is held down at the Somerville Football Oval. And we'll have the marquee set up there, and same sort of thing. It's all day long, but you've got to get in early to set up everything before they lock off access, and then you're sort of stuck there until they let you out at the end of the day, around about 5 o'clock-ish. Then the following week for that, 12th of March, we got Strathayard Primary, who are staying next door at the camp as well, 50 year 6s for that one. Cosmology Discovery Group, the next one was on Saturday the 15th of March. And then the following monthly meeting, like tonight's meeting, is on the 19th of March. And just a note there in the bottom right-hand corner is showing the astronaut, Canadian astronaut Chris Hadfield. He's going to be here in Melbourne, speaking at Hamer Hall on the 1st of July, and the tickets are open and available online. And I know at this stage 3 people at least are going, three members are going, and there may be others that just haven't shared that information yet.
Astromofo number 21, the Vela constellation. So for the new people in the audience, our Astromofo is our monthly photo challenge, where we pick an object or a topic, and members are tasked with capturing photographs of it. And the last one was the constellation Vela. And the first photo I've got up here is one that I took last month of the Pencil Nebula and RCW37 or NGC 2736. is the Pencil Nebula, and also RCW38, which is the glowing area, the hydrogen alpha glowing area, and reflection nebulas over here. So this was a 95-minute exposure with dual band filter, the Optolong L Extreme filter. I'll just mention a couple of things. When we see catalogue numbers for these objects, some of them are NGC, some of them are RCW, some of them are Caldwell or a C, some of them are a GUM. They've got different numbers, and what that is just their designation in a particular catalogue. The NGC is the New Galactic Catalogue, and it includes around about 7,800 objects, so it's a pretty extensive catalogue. RCW is Rogers, Campbell and White Oak catalogue of hydrogen alpha regions in the Milky Way, and they were Australian astronomers who catalogued those, and that contains about 182 objects. GUM is another collection of nebulas as well. It's about 84 emission nebulas composed by Australian astronomer Colin Stanley GUM, and he compiled that at Mount Stromlo in Canberra, and he published that catalogue in about 1955. The nebula that we see in Vela, the big nebula, is actually called the GUM Nebula. He discovered that back at that time. He imaged it with a camera, with a wide field instrument at Mount Stromlo, and that is actually called the GUM Nebula. Other nebulas have got GUM1, GUM2, GUM3. They've got designated numbers, but the GUM Nebula, which we'll see in subsequent photos, was first imaged by Colin Stanley GUM. Okay, so where is Vela? We've got Crux over here, the Southern Cross, and over here we've got Sirius, the bright star in Canis Major. If we draw a line between those two, we pretty much cross through Vela. So Vela is the sail of the Argo Navis, the mythical ship that carried Jason and the Argonauts on their quest for the Golden Fleece. And it's made up of Carina, the hull over here. This is the bow of Carina, the bow and the stern back here. Canopus is the rudder or the steering oar. It's another very bright star, which you can see next to Sirius or across from Sirius when you look south. Then we have Pupus, the stern, the rear deck, and Vela, the sail, through here. So one way to pick out Vela is you can often make out the false cross in the sky, which is this over here. We've got the Southern Cross over here and the false cross over here. And if you find that, on one side of that is Carina, and on the other side of that is Vela. So that's how we find Vela. Okay, this challenge was completed by myself, Chris Kostokanellis, Kelly Clitheroe, Nick Axaris, David Rolfe, Sylvie Grandit and Greg Walton all managed to capture images of Vela. This one here was captured by Kelly Clitheroe with a Samyang 135mm lens and a ASI 533 MC colour camera and an ultimate dual band filter. L-ultimate dual band filter. So it captures hydrogen alpha and O3 emissions, the dual band filter, which are the red areas and the greeny blue areas that you see. And and this over here, the green puffy cloudy bits that you see over here are what's called the Vela supernova remnant. So this is a giant star that exploded some 11,000 years ago, about between 8 and 50 solar masses, in that sort of range. It had to be at least 8 solar masses to explode as a supernova, and less than 50 because we know that there's a neutron star associated with the remnant in Vela. If it was more than 50 solar masses, it would have collapsed into a black hole. And this one also by Kelly. So Kelly's doing a bit of a project with a 135mm lens. So these are fairly wide views. A 135mm camera lens, which most of you would be familiar with, it captures a pretty large chunk of the sky. So this actually is a fairly large object in the sky, and you'd probably need maybe a 25 to 30mm lens to actually capture the whole Vela constellation in one shot. So these are fairly wide views. And this one here is with a 50mm lens. So this captures even more. And that photo there with a 50mm lens, that is roughly the size of the Orion constellation. So if you were to have the Orion constellation, you'd probably have Rigel and, is it Safe up there? And Bellatrix and Betelgeuse down here somewhere. So that is around about the size of the Orion constellation. This one here was captured by me. It is RCW37 or GUM14. 25 exposures with 5-minute exposures with again with the dual band filter, and that is in this photo here. It is this object over here. So this is with a 135mm lens. This is with an 80mm 400mm focal length telescope. So we're able to see the emission areas, hydrogen alpha emission areas here, and there's also a couple of reflection nebulas in there as well. And that's pretty much what the camera looks like for this photo here actually. This is this is actually the GUM nebula. So what I mentioned earlier before, this is again with a 50mm lens, and we've got this hydrogen alpha emission nebula over here, which was captured by Mr. GUM, and then we have the Vela supernova remnant in here as well. And then there's the two other nebulas, the one with the telescope there and another couple of them down there. And that's pretty much what the camera looks like to capture this image here. So it's a short lens, a 50mm lens, a filter draw, and then the camera body there, which I put on an equatorial mount, tracked it and captured 5-minute exposures to create that image. And also down here, you might have remembered the first image, the Pencil Nebula. That is the Pencil Nebula down here with that field of view there. So the 50mm lens here, and then that field of view down there was with the telescope. And we've got more photos of that as well coming up. This one here by Dave Rolfe with a 71mm William Optics telescope, 71mm diameter. 2600 duo camera. So this is a monochrome camera, and Dave's captured what we call luminance frames. So he's no filter on the camera, just capturing the light. He may have a light pollution filter on there, but just capturing the light that comes into the camera. And again, he's managed to capture the Pencil Nebula down here and the Emission Nebula over here as well. There's also a few other clusters and things like that. And the thick star fields that we see are looking across the Milky Way, because this part of the nebula does cross the Milky Way. And then, NGC 2626 by Dave as well. So this is a reflection nebula in Vela as well, and that is in this part of the image here. So this is with, again, with a 70mm William Optics telescope, which I think has a focal length of around 350mm, if anyone, 300 to 350mm, I think the 71 focal length is. And that is the Emission Nebula there, and that's from the same photo. I've just cropped it just to show up that Emission Nebula a little bit better. So another really nice mono image by Dave, and this one here as well, taken with the same equipment again. And this time he's captured this open cluster over here, IC 2395, which is an open cluster over there. This one here is by Greg, and this is a 50mm lens again, but a shorter exposure, 30 seconds. So we don't really pick up a lot of the nebulosity and the supernova remnant with the shorter exposures, but you do pick up a lot of all the star clusters the open clusters that are through here as well. And this is again the Vela constellation, the stars of Vela through here. You've got, in this photo, you've got Puppis up here, and you've got Carina on this side over here. So that's looking at the top of, or the back part of the sail going towards Puppis. And Sylvie Grandit managed to capture this great shot as well. We've got the Pencil Nebula and that Emission Nebula again, and then the clouds of the supernova remnant through here. I'm just trying to remember now where I'll try to pick it out in another photo later on, but I had it picked out where the supernova remnant was. Here we go. Now this one here is by Nick Axaris, and this isn't a single photo, but this is a mosaic of 14 different panels taken by Nick. And he's been working on this image for a few seasons now. So there's a total of 48 hours of exposure over 14 image panels. So this is captured as a mosaic, and he stitched it together to create a single image. So that by using the longer focal length telescope to create the mosaic, he's able to capture a lot more detail. The shorter focal length captures a nice field of view, but because it's a short focal length and small aperture lens, you don't capture as much detail as you do with a larger telescope. So again, he's using the light pollution filters, and the thing is, imaging from Melbourne, in the middle of Melbourne, he's in Glen Iris, I mean, I'm in Seaford, and most of us have got a heck of a lot of light pollution where we are. And using these images, the dual band image, the dual band filters, you're really able to cut out a lot of that light pollution. Sometimes you can even image through the moonlight as well with these filters. So they really do a great job to capture the detail. This is another one of Nick of the supernova remnant, the Vela supernova remnant. Actually, I'll just go back. Now, the actual, the Vela pulsar, which is associated with this remnant, which is the remains of the star that exploded to create the supernova remnant that we see, is situated around about in here somewhere from memory. I was looking at it the other day, and I'm pretty sure I'm pointing to the right part of the photo. So there is a neutron star that's been discovered in around about this part of the photo, which is associated with the supernova remnant. Okay, another one by Nick of a closer look of the supernova remnant with the FRA 300. So this is with a 300mm focal length telescope, and that's about 8.5 hours of exposure and building. So he keeps adding more and more data to this image, and also the Pencil Nebula as well. So this looks like it's with maybe with an FRA 300 as well. And finally, we've got final images from Nick as well. So this is a close-up of the Pencil Nebula taken with a 130mm refractor. So this is with a fairly longer focal length telescope, a larger 130mm aperture, 0.75 reducer. So I think it ends up being around about 800mm focal length. Again, with the filters, the MC Pro camera, and the ASIER. The ASIER is a little computer that everything's connected to capture the image and drive the telescope and guide and whatnot. And Nick uses AstroPixel processor for stacking pics inside in Photoshop for all the processing, but managed to capture really a great deal of detail in the nebula there as well. Okay, our next challenge. We're sticking with Argo Navis. So we're looking at Puppis, the stern or the poop deck of the Argo Navis. So we showed where that was before relative to everything else. And looking again, we've got Sirius over here. So Canis Major and Sirius. And we've got Puppis over here. And this is where Vela was. So most of the images that we saw earlier were from this region. And now we're looking at imaging this region over here. So there's some pretty interesting objects to image there. We've got M46 and M47, which are a notable double cluster, which is around about in this area here. There's a lot of H-alpha regions, a few interesting H-alpha regions in here. Planetary nebula, we've got the Milky Way, oops, let's go back. Got the Milky Way running through as well, so it'll create some really nice wide-angle shots for wide-angle cameras. And yeah, that's our next challenge. So send your photos in, either post them to the Facebook page or eScorpius, or email them to me directly, and I'll include them in the summary. Any questions? Nope. Excellent. Thank you very much.
All right, so sky for the month for the rest of February and the first half of March. And yeah, I also picked Kelly's image there, which was also the picture that was on the monthly Morning Peninsula magazine article that Nerida wrote. All right, let's have a look at the solar system first. So view from the top. And oh yeah, thanks. I think bit less light, that should work better, thanks. So, view from the top of the solar system. This is for, I think, roughly tonight, well, 16th of February, a couple of days ago. So we have the Earth around here, and you can see Venus and Mercury towards the Sun. Mercury is basically now invisible because it's so close to the Sun. And we see Mars up here. And I think when we start the animation, we can see a little bit what that looks like over the next month. You'll see that that Venus will now pass between the Earth and the Sun, so that will mean that it'll get so close to the Sun that we won't be able to see it in about 2 weeks or so, and then reappear on the other side. And Mars is still visible nicely in the night sky at the moment, kind of on the other side of the Sun, so just past its opposition. So well placed for observation there. If we zoom out a bit to the outer planets, I will try to zoom out. If we zoom out to the outer planets, we will see that both Saturn and Neptune are also on the opposite side of the Sun, so very difficult to observe at the moment, or only very close directly after sunset. And Uranus and Jupiter are still in a reasonable position at the moment, so they're still pretty high in the sky. We'll see that in the all-sky view now. So this is for the 1st of March, around 7:30 p.m. So the first thing to notice is that sunset now is around 8 p.m., so getting a bit earlier. And while we're still in daylight savings, well, at least it won't get much earlier than this. But as you can see, Venus, Mercury, and Saturn here are pretty close to the Sun, so you would be able to observe them just after sunset. And Venus is heading towards its inferior conjunction. That's when it's between us and the Sun. And Neptune will also be in conjunction with the Sun on the 20th of March. Mercury is past its, or will be past its superior conjunction when it's on the opposite side behind the Sun, but still too close to the Sun to observe for, I think, all of March pretty much. And Saturn is heading for its conjunction with the Sun when it's exactly on the other side of the Sun as seen from Earth on the 12th of March. So Saturn also won't be visible at all for the next few months. Now, we're currently passing through the plane of Saturn's rings at the moment, and the rings will actually be fully edge on the 23rd of March. So if we could observe Saturn at that point, we wouldn't be able to see the rings at all because they're very thin, and we're looking at them edge on, and they would basically disappear. So as soon as Saturn reappears from behind the Sun after its conjunction, we'll be able to look at it again and see the rings basically as a thin line across the planet, pretty much as it was for the last few weeks as well, if you've had a chance to observe Saturn. So I think it'll just reappear in the morning sky around the end of March or so. So we'll be able to see it again then. All right, if we fast forward, still on the 1st of March to around 10 p.m. to get a good look at the sky then, we will see that Uranus is now pretty low in the northwest and then setting, I think, around 11 p.m. or so. Jupiter setting around midnight, but so that's still well positioned to observe, but it is a bit lower in the sky now. And Mars so we're heading away from Mars at the moment. We're past opposition now, so it's beginning to fade a bit, but it's still around magnitude 0 on the 1st of March, so still pretty bright and setting around 2:30 a.m. But we are getting further away. It's getting smaller and fainter. Looking at the main stars, we can see around 10 p.m. now, the Southern Cross is now again a little bit higher in the sky around that time. And as Chris just mentioned, we have Canopus and Sirius here, and then Puppis, the target for this month's photo challenge, right in the middle there. So and then we have Orion in the northwest, still pretty high in the sky. If we look at the constellations, I think on this slide, yeah, we can see that Puppis is really perfectly positioned for observation for the next month or so. Right? It basically passes the meridian around 10:30 or so. It's very high in the sky, almost at the zenith there. And then for the rest of the night, if we, well, I think this is going to fast forward through the rest of the night. None of the other planets obviously visible. They're all behind the sun at the moment. And yeah, you can see that around 1:30 or so, or 2 a.m. Crux, so the Southern Cross will pass the meridian, and we'll get a bit more of the Milky Way then rising as well. Okay, heading towards sunrise now. Sun is rising a bit later, around 7 a.m. And just quickly looking at the moon for the next month, we will have the new moon on the 28th of February and then the full moon on the 14th. There will actually be a total lunar eclipse, but it won't be visible from Australia. And then we have a new moon on the 29th of March with a partial solar eclipse, but again not visible from anywhere in Australia. Quick look at the apparent relative sizes of the planets for March. Not that interesting because a lot of them won't be visible. But what you can see is that Venus looks absolutely gigantic here because we are at the closest point in our two orbits, right? It's passing between us and the sun. But obviously, we won't see it like this because it is between us and the sun. And yeah, you can see how Saturn's rings here appear as just a very thin line across the planet. Comets brighter than magnitude 10, unfortunately, none. There's nothing in the sky at the moment. There's the couple of comets that were visible are now really fading quite quickly. I thought I should have another look at the asteroid that Peter mentioned in the introduction. So this is you can see the very faint trace of the comet there in the center. So that's from the Very Large Telescope in Chile. So it was first detected at the end of December last year. And as Peter said, around 40 to 90 meters in diameter. And currently, around a 1 in 45 or so chance of hitting Earth in December 2032. But I thought I'd show you the current projection for for December 2032 from NASA's Eyes on the Solar System, or the Eyes on Asteroids. So this one looks like it's passing pretty much between Earth and the Moon, but this has a very large uncertainty in that data. So it could go a little bit to the right or a little bit to the left, and then it'll just hit the Earth exactly. And what I found interesting from some of the discussions around this was to look at those predictions and the probabilities for hitting the Earth. So if this is the current best estimate for where the asteroid will be on that day, then there's this area of uncertainty around it, right? So they don't know by a few, probably 100,000 kilometers or so, where it's going to be. So maybe it's this kind of area that they can currently say, well, it's most likely going to be in this area. And then the probability of hitting the Earth is basically the size of the Earth relative to the size of the area where it might be, right? And so maybe if it's this size, then maybe that's a 1 in 100 chance because the Earth is covering 1/100th of this whole area here. And so now over the next months or then maybe years, they will refine that orbit. And so they'll get a much better idea of where it's going to be. And so the chance of hitting Earth will actually look higher, right? They have a better idea of where it might be. So the area where it might be is smaller. The size of the Earth doesn't change. So in relation to each other, the chance of hitting Earth will actually look higher. Then maybe they do another prediction and we now have this 1 in 40 chance of hitting Earth, right? Because it's 1/40th of the area. But then suddenly they shrink it just a little bit more so that the Earth is now outside of the path and we suddenly drop to 0. So apparently the pattern we're going to see is that the chance of hitting Earth is going to get higher and higher and higher, and then suddenly drop to zero when they can absolutely exclude that we are in the path. So that's the most likely outcome for the predictions. All right, there's one meteor shower, the Gamma Normids, starting on the 25th of February and going until the end of March, peaking around the 14th of March. But the peak will be during the full moon, so probably not that interesting to observe this year. And that's all from me. The sources, as always, are Stellarium, NASA Eyes on the Solar System, and NASA Eyes on Asteroids for this particular one. And then the Heavens Above website and the Astronomy 2025 Almanac. Any questions?
Where's that asteroid at the moment?
Right, I wanted to include the current one. It was pretty close to the Earth at the end of December last year when they discovered it. Okay. And so it's basically heading away from us, still between us and Mars, I think. Yeah. And so at the moment, I think it's still observable with the really big telescopes, right? But it's only maybe 50 meters or so it's very, very dim. So they already had to use the VLT, which is one of the biggest telescopes that's available to actually get some images. But yeah, I think it's not even past the orbit of Mars at the moment. I'm not even sure if it's going past that orbit, but it's still relatively close to Earth at the moment. And its orbit will come past the Earth again in about 4 years' time, and then, or 3.5 or 4 years' time. And so by then, they will be able to use radar observations to get a much better idea of its size and exact orbit. Yeah. And so then they will know whether the next time will be a hit or a near miss.
How is it different from a comet? Because comets come.
Yeah, right. So the difference to a comet is that this one's not going that far out into the solar system. So it's a bit more like the asteroids, for example, between Mars and Jupiter, that are kind of staying in that general area, whereas the comets are coming from much, much further out, and then coming in and going much further out again.
And it's not showing off tails and...
No, I think also that's right. So also the material is different. So this is probably just like a rubble pile or something like that. So it doesn't have a lot of volatile material like ice and water and so on. So that's why it doesn't create a big tail when it comes closer to the sun. Also, this one, I think, doesn't come as close to the sun as many comets do.
Guido, presumably it's coming, every time it orbits around, it's coming slightly closer to the Earth. So if it doesn't miss us in 2032 or whatever, the next time around it'll be further away again? Progressively further away again?
That's a good question, whether the orbit... like how the distance to the Earth changes with each orbit. I'm not sure. So I'm not sure how close, like whether the distance is close enough that Earth's gravity will change the orbit significantly or not. I don't know. But I think this is a bit more like, because it's on its own orbit around the sun, and it's just that our orbit and its orbit are close together, a bit like every couple of years we are at the closest point in our orbit to Mars, for example, right? So it's more like those kinds of situations. But yeah, whether Earth's gravity actually at that distance where it passes has a significant impact, I'm not sure. Must have some impact, but I don't know how much it changes.
So could we have a problem 4 years later again?
I think the problem at the moment is that we don't know the orbit precisely enough. So if we knew the orbit really precisely, we could predict it for hundreds of years into the future, probably. So then we could just exclude it completely, most likely. But because there's so much uncertainty in the orbit, because they only discovered it in December, and now it's already too far away to really measure anything. I think that's why there's this uncertainty at the moment.
Now we come on to the main talk tonight by this gentleman, Professor Kip Thorne. Back in 2018, there was actually a chance of him coming down to the Briars as he was scheduled to come back to Victoria. But as it turned out, he had other things on and called off his Australia tour, and we had Oliver James from the Interstellar movie come down to visit us instead in that year. Now, Kip Thorne is absolute giant in theoretical physics. He's the co-founder of the LIGO observatories. So in other words, he was the one that came up with the original idea. This is the laser interferometry for detecting gravitational waves. And just about 18 months after this this talk was given, he was awarded the Nobel Prize once they did actually confirm the existence of gravitational waves. Now, I assume some of you here have seen the movie Interstellar. If you haven't, it's one that you ought to check out from 2014. Kip Thorne was actually the executive producer and science advisor of it. And the other gentleman I mentioned, Oliver James, who came down to visit here, was also involved in the animations of the supergiant black hole called Gargantua in that movie. Now, this public lecture was given at Monash University towards the end of 2015. It's hosted by their head of school, Professor Michael Morgan, and there's a couple of minutes introduction by Professor Alan Finkel. And the next year after this talk, he moved on from Monash University and became the chief scientist of Australia, so the government chief scientist, where he kept in that role for a number of years. Then this talk, so the talk goes for just over an hour, and then there's about 10 minutes of questions afterwards. So after the talk, we'll then close, and because it's such a lengthy talk with questions, feel free to get up and go out and help yourself to a cup of coffee any time. Just quietly do so if you can. Oh, and one other thing to note is that a couple of times during the talk, he shows to the audience in the room some excerpts from the Interstellar movie. And for copyright reasons, Monash University couldn't record those and show them, and similarly we can't record them and show them, so you'll see him talking to a fairly blank screen at that stage for a minute or two, just so that you'll actually know what's going on there.
Tonight we have a guest speaker who is an acknowledged expert, a giant of modern physics, but also a superb communicator of physics to the general public. Professor Kip Thorne received his bachelor's degree from Caltech and his PhD from Princeton University. I won't say what year, Kip, but it was a while ago. After returning to Caltech, he became the Professor of Theoretical Physics, the Feynman Professor of Theoretical Physics, and the Feynman Professor Emeritus, starting in 2009. Professor Thorne has been awarded the Lilienfeld Prize of the American Physical Society, the Karl Schwarzschild Medal of the German Astronomical Society, the Albert Einstein Medal, these are good names, the UNESCO Niels Bohr Gold Medal, and the Commonwealth Award for Science. He co-authored the textbook Gravitation, from which most of the present generation of scientists have learned general relativity theory. His popular science book, called Black Holes and Time Warps, Einstein's Outrageous Legacy, received the American Institute of Physics Science Writing Award, the Phi Beta Kappa Science Writing Award, and the Russian Priroda Reader's Choice Award. Very impressive. Remarkably, I found out this evening he was the co-founder of the LIGO experiment, the experiment to detect gravitational waves, and is nurturing them along the path to the next generation of LIGO that will actually do the detection of gravitational waves. But of course, what we all know is that most recently, Professor Thorne was the scientific advisor and the executive producer of Christopher Nolan's 2014 film Interstellar, the one that Michael was just waving around. Now, my wife and I, Elizabeth down here, we saw the movie Interstellar twice. And I've got to say that helped enormously because the plot is very difficult. Why? Because things happen at the beginning of the movie that actually don't happen till well into the future and well into the movie. So the second time round, we caught on. We were a little slow the first time round. But both times we enjoyed the magnificent renditions of how black holes might appear. But I admit that even the second time round, I still found the mathematical illusions and symbolism difficult. And to a lesser degree than most of you here, I am trained in physics and maths. Wasn't difficult because Kip and the directors didn't do a good job. It is just tough. So I am very much looking forward to learning from Kip Thorne tonight the secrets of black holes, of relativity, the Big Bang, and perhaps the meaning of life. Thank you, Kip.
Thank you very much. I recommend seeing it 5 times. The central theme of my talk is a century of relativity, as I'll describe. November 25th, 1915 was the date on which Albert Einstein gave us his theory of relativity. So we are coming up on that very soon. I'm to give this same lecture in Berlin on November 25th, 2015, on the centenary date for an audience like yourselves. And so you're getting the first dry run at the centenary lecture in Berlin following Einstein's work. But because Interstellar is a wonderful vehicle for explaining some of the ideas that have followed from Einstein's work, I want to begin with a preamble of a few words, in fact, a little film clip about Interstellar to sort of set the stage for that aspect of the talk. And so, let's see how this goes.
We're still pioneers. We've barely begun. Our greatest accomplishments cannot be behind us, because our destiny lies above us.
The initial impetus for the project had been to say, why not examine real possibilities? Why not actually look at the real science there?
Luckily we had Kip, and Kip is the foremost authority on all things gravitational.
Slight exaggeration.
The space inside here scatters some of it back, light scattering off of the surface of the Ripple Ocean. Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time the depiction began with Einstein's general relativity equations.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's mathematical data and they created real visual representations of what a black hole is meant to look like.
The collaboration has produced visualization of things which nobody had ever managed to do before. You know, we potentially may have discovered a couple of new things that were lurking there inside the mathematics, inside the physics.
I worked out the equations that would enable him to do the gravitational lensing. So you have light that comes from a star behind the black hole. It may come in, go around the black hole several times, and then come to the camera. And so you wind up with several different images of the star.
The black hole warps the space so much, it just looks like you're looking at a strange sort of funnel in the sky with this intensely black circle at the middle of it. But the gravity of the black hole draws in all the matter from the surrounding universe. And this spins out into a giant disk around the central sphere. And as it whirls in towards the center, the gas gets hotter and hotter. And this thing, the accretion disk around it, shines brilliantly. And then we found that if you then render this whole thing, you visualize it all through this extraordinary gravitational lens, the gravity twists this glowing disk of gas into weird shapes, and you get this extraordinary sort of rainbow of fire across the top of the black hole.
And I saw this disk wrap up over the black hole and under the black hole. I'd known it intellectually, but knowing it intellectually is completely different than seeing it, than feeling it.
We had determined when we started down this road that if it didn't look like something that would be comprehensible to the audience, we would have to manipulate it in some way. But what we found was, as long as we didn't change the point of view too much of the camera position, we could get some very understandable tactile imagery from those equations. They were constantly surprising. Spoke to the maxim that truth can be stranger than fiction.
We're going to write several technical papers about this. One aimed at the astrophysics community, and then something for the computer graphics community, saying, here are some things that we've discovered about gravitational lensing by rapidly spinning black holes that we never knew before. So this collaboration isn't over until we've given some sense of the things that we've learned.
So that was a film clip that was used, done in connection with Wired magazine before the movie came out, slightly before, as part of the PR for the movie. But I show it to you to indicate that you are seeing Christopher Nolan, who controls things with an iron fist, and his wife, who is the Iron Lady of Hollywood in terms of her controlling nature. You see Jonathan Nolan, his brother, who's a screenwriter and a very powerful figure in Hollywood, into himself as well. And Paul Franklin, who won the Academy Award for the visual effects for this movie. They totally embraced the idea of doing a movie that was steeped in general relativity. And they worked closely with me to make it happen. And I have to say it was one of the several most wonderful collaborations of my life. And for Hollywood to embrace something as weird, as abstruse as general relativity, and make a movie that sells 100 million tickets worldwide about general relativity, that says something about modern culture, I think, something very positive about modern culture and about what the general population of the world is willing to embrace if it is done very well. So I don't know what's happening. Here we go. Okay. So I now want to move on. That was by way of a preamble, and now I have a prologue that I call Einstein's chutzpah. And so this is about how Einstein got to general relativity theory. So Newton and Einstein are the two great figures stand out above everybody else in the history of physics. Newton gave us a framework for the laws of nature that has lasted for 200 years. A framework based on the idea that space and time are absolute, non-controversial. Everybody sees space and time behave the same way. It's a framework that deals with forces and accelerations and the things of everyday experience. Einstein came along several centuries later and gave us a new framework that's now been in place for 110 years. So this is 10 years before general relativity. And it is a framework based on a new principle, the principle of relativity, that says that all the laws of nature must be the same in every freely moving laboratory, everywhere in the universe and at all times in the universe. The laws of physics are the same as you would see them, as anyone else would see them. Even somebody inside a black hole will see the same laws of physics. And this then is basically a law that governs the laws of physics. That's real chutzpah. That really takes a lot of self-confidence to lay out and say, here is the law that governs all the other laws of physics. And that's what it was. And it had weird consequences. For example, if I measure the speed of light and I get a number that's about 300,000 kilometers a second, and if you're in your sports car moving at 200,000 kilometers per second in the same direction as this light beam, you would have thought that the speed of light you would measure would be 300,000 minus 200,000, be 100,000 kilometers a second, obviously, but it's not. You measure that same speed as I measure. And that just seems absolutely impossible. How could that possibly be? And the answer, it turns out, is that you and I disagree about the lengths of things. We disagree about the duration of time that occurs. We disagree about what it even means for two events to be simultaneous. We disagree in ways that can be analyzed with Einstein's equations, and that you can build up intuition about it. But that's what relativity means, that the ideas of space and time, simultaneity, they are relative. They're different for you if you are moving relative to me. They're different for you if you're at a different location in the universe from me. And so you can get queasy as a physicist until you finally master the ideas that connect what you would observe and what I observe. And then Einstein, having promulgated the principle of relativity, having concluded that space, time, and simultaneity are relative, different, they're personal for different people moving in different manners, he then looked at Newton's law of gravity. Newton said that there is a gravitational force that the sun exerts on the Earth that is proportional to 1 over the square of the distance between the sun and the Earth. The distance, the instantaneous separation of the sun and the Earth. You measure where the sun is and the Earth at that same moment of time, and you measure that distance. But the problem, of course, is that Einstein tells us that separation d is different as measured by the sun than as measured by the Earth. So whose separation do you use in Newton's law? And instantaneous, well, simultaneity is different as seen by the sun and the Earth. So how do you even formulate this? Einstein looked at Newton's law of gravity and said, Newton has to be wrong. Your law of gravity, Isaac Newton, violates my fundamental principles of relativity. And so we have to reformulate the fundamental law of gravity. Newton must be wrong. And so I move on. That was Einstein's chutzpah. And now we have a whole new description of gravity due to Einstein. This is 1912. It's not yet relativity. It's not yet November 25th, 1915, but it's his first big leap in understanding gravity. It's what I like to call Einstein's law of time warps. It says that things like to live where they will age the most slowly. Wouldn't you like to do that? And gravity pulls them there. And it's a quantitative equation that says if time passes more slowly on the surface of the Earth than up at very high altitude by 1 second out of a century, then, and you go in and you look at the formula that Einstein gave us, that accounts for the gravitational pull that holds us to the surface of the Earth. So 1 second in 100 years, slowing of time on the surface of the Earth causes the gravitational pull that we feel. And that's really incredible, that that tiny amount of slowing of time causes gravity. The Earth's mass warps time, and the warping of time then produces gravity, according to Einstein in 1912. And this has been verified by flying atomic clocks up to high altitude, the first really high precision experiment back in 1976. And it was verified to an accuracy of 1/100th of 1%, 1 part in 10,000. Enormously accurate, just like Einstein said it had to be. Einstein makes the prediction in 1912 that time has to be slowed down by that much because he knows how strong the gravity is on the surface of the Earth. It takes more than 50 years until technology is good enough to verify it. But it gets verified. And you see this in Einstein time after time. He makes predictions and technology is not good enough to even test them for 50 years. 50 years later, they're part of everyday technology. The laser is an example. The fundamental physics that underlies the laser was conceived by Einstein back at about the same era. The first laser was built in the 1960s, and you now have them at the checkout stands in grocery stores. And so that was Einstein. You ask who is the greatest physicist of all time, there's a debate. Was it Newton or was it Einstein? I would lay my money on Einstein, actually. But maybe I'm prejudiced. He's a little closer to my era. Near a black hole, such as Gargantua in the movie Interstellar, gravity is enormously stronger, so the slowing of time is enormously greater. And so in the movie Interstellar, there is a planet called Miller's Planet that's in orbit around a black hole, very close to the surface of the black hole. The black hole's name is Gargantua. And 1 hour on that planet is the same as 7 years on Earth. That's an enormous amount of slowing. And that is the source of huge tension and emotion in this movie, for those of you who have seen it. Cooper, played by Matthew McConaughey, and his daughter Murph, they meet just before he goes off into space, and he knows he's going to go near a black hole, and he tells her that she's going to grow up and maybe be as old as he is before he comes back. And for him, it will be a small amount of time. We see him go near a black hole. He lingers there necessarily because of things that you see in the movie for a couple of hours. When he has emerged from being around the black hole, he gets TV transmissions from his daughter, and this is his daughter. He's aged now a matter of hours going down near the black hole, And she is now a mature woman and a brilliant theoretical physicist. This is one of the things I love about this movie. The stars are all theoretical physicists. Then he goes near the black hole once more for plot reasons in the movie. And when he comes back, this is his daughter. And he, by that time, has aged a total of a couple of years. And his daughter is a very old woman. And the emotion of this really comes home in this film. And this is Einstein's law of time warps in action in a movie for 100 million people. Now, in 1912, Einstein realized, having understood gravity this way, that if time is warped, then space must also be warped. I won't explain his reasoning, but it's a very compelling reasoning. And it was also in 1976, that same year, that the first really high precision measurements of the warping of space were done. In this case, it was the Viking spacecraft. There were two of them in orbit around the planet Mars. And Mars carried them almost behind the sun relative to the Earth. And so radio signals were sent out to these Viking spacecraft and transponded back to Earth. And the round-trip travel time was monitored as the spacecraft moved nearly behind the sun. And you knew what, from knowing the orbit, you knew what that round-trip travel time should have been if space was flat between here and there. And there was an extra time delay of microseconds, 100 microseconds, 200 microseconds, going way up as it is almost behind the sun and then coming back down. And from that you knew that space had to be warped in a manner I describe here. And this is the first of a set of diagrams I'll use to describe the warping of space. What I imagine is taking the orbital plane of the spacecraft. The orbit the spacecraft is moving in around the sun. That's a two-dimensional plane. And space is warped by the sun's presence. In order to see that warping, I take that plane out and I put it in a flat space. And it has to bend down in order to see the warping. We call this an embedding space, but I'm going to call it also the bulk or hyperspace, which is a physicist's modern name for it. And I'm going to tell you later in this talk that we think the bulk is real, that there really is a higher dimension, and that our universe really is warped in that higher dimension. If you do that, and then you imagine you're a higher dimensional being that lives in the bulk. You live in the higher dimension and you look in. It's a bulk being. And the bulk beings play a huge role in Interstellar. Through the early part of the movie, they are simply called they, with a great deal of reverence. They. And then, this is typical of Christopher Nolan, nearly at the end of Interstellar, just once, the word bulk being is used, just to clue in those few people who know what a bulk is. And the word bulk being reveals who they are, that they are living in this higher dimension. Anyway, so imagine you're a bulk being, you're looking in from the higher dimension. That's the warping of space that you see. And there's this extra time delay because the signal has to travel that larger distance bending down through that warped space. And from just measuring that extra time delay, you can compute the warpage of space around the sun just directly. And then Einstein, once he had his general relativity equations a few years later, he could predict what it is. And again, you get a wonderful agreement at a level of a part in 10,000 between what is predicted by general relativity and what was measured in 1976. So by 1912, then, Einstein understood, believed, had convinced himself that space is warped and time is warped. And he then struggled for 3 years to master the mathematics that was required to build a new set of physical laws to describe this warping, mathematics of what we nowadays call differential geometry. And at the end of that 3-year struggle, he announced on November 25th, 1915, an equation that we write symbolically in this way. It looks deceptively simple, but that is the equation that governs all of the warping of space and time by the energy that is present in the universe, by the energy and momentum, to use technical terms, that are present in the universe. It's called Einstein's field equation. And it describes then how space and time are warped by mass and energy. And then from it you can also deduce how this warping controls the motions of stars and spacecraft and light and everything else. It's just a marvelously beautiful theory mathematically for those, once you learn the abstruse mathematics, and powerful, tremendously powerful, and that's what the rest of my talk is going to be about. What has Einstein's equation taught us in this past century, in this, the centennial year of general relativity? Let me begin with black holes. A very brief history of black holes. There are going to be some names here that won't be familiar to you. I don't want to focus on the names so much as on the issues. 1916, beginning with Einstein's field equation, that one equation which has ever so much information buried in it. A guy named Karl Schwarzschild discovered the formula that describes a black hole, a non-spinning black hole, but he didn't understand it. He didn't understand what he had. 1939, Einstein looked at Schwarzschild's formula and he completely misunderstood what it was saying, and he disbelieved that black holes could exist because he didn't really understand. That same year, Robert Oppenheimer, who would go on to lead the atomic bomb project in the United States in World War II, and his student Hartland Snyder, who had been a truck driver in Utah in the United States until he went to work with Oppenheimer. Together they solved Einstein's equations to compute what happens when a star implodes, if it loses the pressure that holds it up when it implodes. And they saw it forming this Schwarzschild's black hole, but they didn't really understand the mathematics, and they couldn't really fully decipher what was going on. And it was not until the 1950s and 60s, in the hands of a number of subsequent generation of physicists, including John Wheeler, who was my personal mentor at Princeton, finally the equations were understood and the things I'm going to describe were understood. In 1965, Roy Kerr in New Zealand discovered the formula for spinning black holes, and so it brought in spin, which will be very important in what I described for you. In the 60s and 70s, we had then the golden age of black hole research led by Stephen Hawking, and my own students at Caltech made major contributions, and I stood by and smiled and admired them. I was thinking about gravity waves at the time. I'll talk about gravity waves at the end of this talk. And in the 1970s, we began to get observational evidence for black holes. This whole thing is a little more than half a century until the predictions of the mathematics were understood and the marvelous things that I'm going to describe came out. So if I'm a bulk being, I look in at a black hole, I see a warped space that's not this gentle warping, but it's a huge amount of warping. This is the warped space around a non-spinning black hole. The horizon is down here. It's a circle. That's the surface of the black hole. It's a circle because I'm only looking at a two-dimensional plane through the black hole, a two-dimensional surface through the black hole. If I restore the third dimension, which is awfully hard to do when you're a human trying to pretend to be a bulk being and looking in from the outside, if I restore the third dimension, that circle becomes a sphere, and the black hole is spherical, slightly flattened if it is spinning. This color coding depicts the slowing of time. When it goes from green to red, time is flowing at 10% of the rate of flow of time far away on Earth. As seen by a bulk being, if the black hole is spinning quite rapidly, the throat of this warped space becomes deeper. But the color coding for the slowing of time isn't changed much. But what happens is that the spin of the black hole drags space into a whirling motion around the black hole with an angular velocity of whirl that's proportional to the length of these white arrows. It's fast near the horizon, slow farther away. It's very much like the air in a tornado, which is faster near the core of the tornado and slower farther away. But instead of it being air that's whirling, it's space that's whirling. If you go down near the black hole, you're grabbed by that whirling space, and you cannot prevent yourself from whirling around and around and around any more than a straw caught in a tornado can save itself from whirling around and around. But that is what a black hole looks like as seen by a bulk being. And we're not bulk beings. We live in this membrane. We live in this surface. where I should restore one more dimension, but I can't do it and visualize that on a screen. And so if you have a camera sitting here and there's a star there, you can get light rays from the star that come around the black hole in this direction, or a light ray that comes around in that direction. And so you see two images of the star from light rays that come around in the two sides. This is called gravitational lensing. The light rays are bent just like light rays are bent in a telescope mirror, or are bent in a telescope lens or by a mirror. And so Alain Riazuelo, a close friend of mine in Paris, made this image by putting a camera there and doing computations on a computer to simulate the propagation of light from this star and other stars around the black hole, and got an image that looks like that. And you see the black hole's shadow here, which corresponds to the region where no light rays can get by because the black hole is in the way. So you see the circular shadow, and these are the two images of that particular star. And so this was the inspiration for what we did in Interstellar. So in Interstellar, Christopher Nolan, and this was described in that little film clip, he said to me, I want you to work with Paul Franklin to make accurate astrophysical images of what a black hole really looks like, and the gravitational lensing by a real black hole. Paul put me together. He's the founder, co-founder of Double Negative, a graphics house in London. Put me together with Eugenie von Tunzelmann, Oliver James. Oliver is the chief scientist there, and Eugenie von Tunzelmann is one of the lead artists. And we worked together to produce the images that you see, and then people who worked under them, with them. I fed them the equations. They made the images from the equations. And this was a significant contribution to Paul's winning the Academy Award. It's his second Academy Award working with Christopher Nolan for visual effects. The first one was for Inception. And so I'm going to show you what Gargantua, the black hole in the movie, looked like in one of our early simulations before we put a disk of hot gas around it. And this is what is also discussed in that film clip. In here you can see things that nobody had ever seen before. And we did publish a paper in a scientific journal called Classical and Quantum Gravity, which describes some of the things that we see. The camera now is going to orbit around the black hole. The black hole is spinning. This is the edge of the black hole that is heading toward us. That's the edge that's heading away. There's some interesting structure on the side that's heading toward us that has to do with details of the gravitational lensing that we discuss in this technical paper in Classical and Quantum Gravity. But as I told you, there are two images of every star. Not just two. It turns out that we see as many as 14 images of an individual star, the same star. And these images are created in pairs and then they annihilate in pairs due to what are called caustics or catastrophes in gravitational lensing. And this is a technical subject, but a very pretty and interesting subject. But if you look close to the edge of the black hole shadow, you will occasionally see suddenly where there was no star, a star appears and then it breaks apart and it's two stellar images that are produced by this gravitational lensing. So this is what it looks like as you orbit around and around the black hole. You see an overall flow of stars from left to right. They are sort of repelled by the black hole, except there's a second set of images inside here that are flowing from right to left. Down inside, below there's another set flowing from left to right. And down in here, you occasionally see these pairs of images created. And if you watch, you also see pairs of images annihilate. But it's really a very pretty thing. And this is what a camera would see in orbit around a black hole, precisely what a camera would see in orbit around a black hole. But this is not what you see in Interstellar. This is what you see in Interstellar. And it's quite different because there's a disk of hot gas orbiting around Gargantua, the black hole, and it's radiating very, very brightly. And the brilliance of that gas emitting light is overwhelming the light from the stars. So if you look really closely in the movie, not in this image, you can see a sprinkling of stars out there. But it's just, you're overwhelmed by the brilliance of the gas. And you look at this, this is sort of an iconic image from the movie, and it's an iconic example of gravitational lensing, and it's very easily explained. So the disk is rather like Saturn's rings. And here's the black hole, that's Saturn's rings if there were no lensing. Here is the camera. And if the camera looks at the front of the disk, well, the light from this disk just comes to the camera and looks perfectly normal going across the front of the black hole. But if it looks upward, it will see a light ray that came from the top of the back side of the disk. And so the top of the back side of the disk looks to the camera like it's up here, wrapped around above the black hole. Because the light rays from back here are all coming up over the black hole and down in, so the camera looks up and says, well, that's where the disk is. And similarly down here, the camera looks down and it sees a light ray coming from the bottom of the back of the disk. And so the bottom of the back of the disk looks like it's wrapped around the bottom of the black hole, and so this is what the accretion disk around Gargantua looks like. There's one additional twist. This is an awfully blurred image, and that's because Christopher Nolan insisted it's not your eyes that are looking at this, it's an IMAX camera. And this light is so bright that when it goes through the IMAX camera, some of the light scatters. Some of the photons of light scatter inside the camera, and they make this glare. And so they very carefully modeled, they simulated what happens when the light from that disk goes through the camera to produce this glare. And so this is what you see is what an IMAX camera would see, not what you would see with your own eyes if you're up near a black hole. But this is general relativity writ large in Hollywood. Where do these disks come from? Well, they're produced when a black hole tears a star apart. This is a computer simulation by a pair of young astrophysicists, postdoctoral students who did this. You have a black hole that you may be able to see up here. It's faint blue. And a star is going to come in, go very near the black hole, swing around it, and get torn apart. And you're going to watch what happens to the star when it gets torn apart. So here it comes around, it's torn apart, and some of the gas gets caught in orbit around the black hole, is trapped there to form a disk, which becomes ultimately the kind of a disk that you have in Interstellar around Gargantua. A large fraction of the gas just goes flying away in a jet. This is a black hole roughly like the one in Gargantua. This whole process requires many days to happen. And you wind up with the kind of disk that you see in Gargantua. The Gargantua's disk is actually quite old and quite cold compared to disks that are normally seen by astrophysicists, by astronomers around black holes. There actually is a black hole that weighs 4 million times what the sun weighs at the center of our own Milky Way galaxy. At night, if you look in the constellation Sagittarius, you see the center of our galaxy. And in the center of our galaxy, there is a 4 million solar mass black hole. Andrea Ghez at UCLA and her team have done observations of stars orbiting around that black hole over a long period of time, beginning in the 1990s. They've collected about 20 years worth of data. And these are the orbits that you see, and this is a simulation where she shows where the star actually is, each of these stars as time goes on over the period from the beginning of their observations to the end. The black hole is up in here. If you just watch, for example, this star comes in, it whips around the black hole. You see star after star in here whipping around the black hole that's down there at the center. And you can weigh the black hole, see how heavy it is just by the orbits of those stars that are trapped orbiting around the black hole, come in like a comet going around the sun, whip around the black hole, go out, in, whip around the black hole, go out again. So we have very detailed observations of black holes in that sense. We don't see the black hole itself, but we see its gravitational pull on stars. So what are the prospects to actually see an accretion disk around a black hole, to image it, and the shadow of the black hole against the accretion disk like in the movie? I would have thought it was hopeless, but it turns out it's not. Black holes are so small and they're so far away from us that to actually image that with a telescope seemed to me until recently to be totally hopeless. But there are radio astronomers who figured out otherwise. And so for that black hole at the center of the Milky Way galaxy, they have put together something called the Event Horizon Telescope, which combines data from many, many radio telescopes worldwide, including, of course, Australia, which really is the pioneer in radio astronomy and a major force in radio astronomy still many decades later. It's a collaboration of hundreds of radio astronomies from 34 universities and institutes around the world. Here are a few of the radio telescopes that are used. And looking at where they are, how close they are to doing this imaging, I would say success is likely in this decade. They are within a few years of actually being able to build an image like the image that you see in Interstellar of the accretion disk and the shadow of the black hole in the center of our galaxy. A few words about black hole weirdness is illustrated by Miller's planet. In Interstellar, Miller's planet is the planet that's very close to the black hole. It's the planet where Cooper and his team go down and they spend a couple of hours there, and 1 hour on Miller's planet is 7 years back on Earth because the planet's so close to the black hole Gargantua. This is a image from the movie with Miller's planet, the accretion disk, and Gargantua. Now, if Gargantua were not spinning, and this is a picture then of what it looks like to a bulk being looking in from the outside, if it were not spinning, the closest Miller's planet could be to the black hole would be up here. The problem is, if it's any closer than that, its orbit is unstable. A tiny, tiny force of any sort would cause the orbit, cause the star to spiral into the black hole and get swallowed. And it's unstable, like standing a pencil on its tip. It will fall over. Anything at all will knock it over. And so for this innermost stable orbit, 1 hour on the planet is 1.5 hours on Earth. And I knew this when I was working with Christopher Nolan. He announced to me in one of our earlier meetings, I want 1 hour on Miller's planet to be 7 years on Earth. And I said, it's impossible. General relativity will not allow it. And he said, you've been wrong before. I've seen you be wrong before. My brother has seen you be wrong before. Go home and do the calculation. And so I went home and I did the calculation. I was wrong. It is possible. But the black hole has to spin very, very fast. The whirl of space will stabilize the orbit. Basically, centrifugal forces associated with the whirling of space manage to stabilize the orbit so it can be there nice stably going around and around very near the black hole's horizon, way down here if the black hole is spinning fast enough. But fast enough, there's a maximum spin that any black hole can possibly have. You have to be this close to the maximum spin. Oh, not 99%, not 99.9%, but 15 nines. But it's possible in principle. In practice, any black hole spinning that fast would almost certainly be spun back down quite quickly by swallowing matter that slows it down. I mean, I did research on this myself back in the 1970s. But for Hollywood, if it's allowed, then you can go with it if it makes for a great story. And so this makes for a great story, and so you stretch things. You don't stretch what's allowed, but you stretch what's likely to occur in the real universe. And so that's what happened with Interstellar. On Miller's planet, you have 1 kilometer high water waves. Here's a film clip.
How long for the engines, Case?
A minute or two.
Well, we don't have it. Helmets on! Brandon, co-pilot, you're up. Case, load cabin oxygen through the main thrusters. We're going to spark it.
Roger that.
Lock! Depressurizing! Engines up!
So where did those giant water waves, 1 kilometer high water waves, come from? There's a hint in the film that they come sequentially, about 1 every hour. And so you see 2 of them with about 1 hour in between. And so you can then go do a little calculation, which I did, which underlies the 1 every hour, except I have to tell you, Christopher Nolan said 1 an hour before I did the calculation, and the calculation worked out just right. And so somehow he has an intuition like Einstein in some situations. So the story is that the Earth is deformed by the pull of the moon. The side of the Earth that's closer to the moon is pulled on more strongly than the side that's farther away from the moon. And this causes the oceans to bulge, which gives rise to the tides of on the oceans. Well, similarly, Gargantua, in this diagram of the bottom part of what would be seen by a bulk being, Gargantua exerts the same kind of tidal forces on Miller's planet, the deformed Miller's planet, stretch it radially toward and away from Gargantua, which is down here, and squeeze it from the sides gravitationally. If Gargantua was then trapped into this orbit fairly recently, and it may still be rocking back and forth and settling down into its final state where it will be keeping the same face toward Gargantua at all times. That rocking period turns out to be 1 hour. If the mass of Gargantua is 100 million suns, but 100 million suns is also just precisely the mass you need for Gargantua to deform the planet. So I can get the mass by what's required to deform the planet strongly in order to get this rocking to occur. And then I can verify it by the rocking period. But the key point of the physics is that as the planet rocks back and forth, the oceans slosh. They just slosh. This is the analog of what's called a tidal bore, when the tides on the ocean go up, rushing up a river, and you get a front that can be as high as a few feet on a few rivers in the world. But normally it's tiny, a tidal bore. These are 1 kilometer high tidal bores on a rocking planet. But this I tell to you because in this movie you have wonderful examples of being able to just make observations of what you see in the movie, and then if you know some of these laws of physics you can figure out what's going on quantitatively. We have measured the mass of Gargantua. It's 100 million times the mass of the Sun. You can then compute that its orbit is the same as the circumference of its orbit is the same as the circumference of Gargantua is the same as that of the Earth's orbit around the Sun. And we know it's spinning very fast. And so we've gotten all of this out of just looking at the properties of Miller's planet. So it's really quite wonderful. I'm going to skip over this and move on. Inside black holes are singularities governed by quantum gravity. And this also shows up in Interstellar. Let's begin with the horizon of a black hole. That's the surface of a black hole. Einstein's law of time warp says that if you hover right at the surface of the black hole, at the event horizon, the gravitational force you feel is infinite. And that means that time has slowed to a halt there, if you hover there. It's not flowing at all. That's really rather remarkable, but then even more remarkable is the question, well, what happens inside a black hole? What can be slower than stopped time? And the answer when you go to Einstein's mathematics is that time inside a black hole is flowing downward away from the horizon in a direction you would have thought was a space direction. And as a result, everything inside the black hole is dragged downward by that forward flow of time. Nothing can move backward against the flow of time, and that's another reason why nothing can get out of a black hole. So a really very weird thing. And once you get down, and then I want to say, and so in the movie, for plot reasons, Cooper and the robot TARS plunge into the black hole. They plunge into Gargantua. And I want to show you a piece of a film clip of what Cooper sees when he begins to fall into the black hole. So that's his spacecraft. Now you're seeing it from his spacecraft.
Approaching the event horizon. Port side, dipping down beneath it. You go through it.
So he's now down inside the black hole. He tells you, I've gone through the event horizon. And you're looking back and you see the external universe. Light cannot get out of the black hole, but it can go down into the black hole. And if you're inside the black hole, you can look up and you can see the external universe. But it's a little peculiar. This is the accretion disk now around Gargantua. The external universe, and it's sort of about that size, and the external universe is inside the accretion disk and Gargantua is outside. Things are sort of turned inside out. As the external universe subtends a small ring on the sky, and the interior of Gargantua subtends everything else. And it's just marvelous to see in this movie. I mean, I had not told them what they were going to see. They made this film clip without my advice, but they were good enough by then that they did it right. They used the equations of general relativity, and they got it right. And this is what you see from inside a black hole, is looking out into the external universe. Inside Gargantua, again in diagrams as seen by bulk beings, there is a singularity, a wildly chaotic singularity. It's governed by the laws of quantum gravity. These laws are likely to be some variant of what we call string theory, and they've been the holy grail of theoretical physics since 1960. They control not only the singularities inside black holes, they control the birth of our universe. They control whether or not you can have time machines for backward time travel. It turns out that it's very likely that time machines will always self-destruct if you try to make one. But it's the laws of quantum gravity which govern whether or not this self-destruction actually occurs. These laws of quantum gravity are so powerful in answering some of the most interesting questions that we would like to know answers of that I just wait eagerly for people who are smarter than me to bring those laws of quantum gravity under control. And I think that they are within a couple of decades or so of doing so. But those laws of quantum gravity play a major role in Interstellar. They're called quantum data in the film. And I'll let you just watch the movie and see how the reason that Cooper and TARS go inside the black hole is to learn the laws of quantum gravity by making observations of the singularity inside. And then to carry that knowledge back out in some manner in order to use that knowledge to save the human race. And it turns out, I'm not going to go into detail, there are 3 singularities inside the black hole. There are 2 gentle ones and this vicious one. And Chris very carefully chose that Cooper gets caught by the outflowing singularity, which is the most gentle of them, and he manages to survive. And so I'm going to say just a few words about that. But first I want to turn to the next topic, which is into the bulk. So everything I've told you up until now is stuff that is really quite firm. Even the stuff about the singularities inside black holes. General relativity, we've worked long enough with those equations as physicists that we really understand the singularities inside black holes, except for their quantum core, except for the core part of the singularity that's governed by the laws of quantum gravity. But everything up to there we understand. We understand black holes quite thoroughly by now. But the bulk that I referred to, this higher dimensions, this is now speculation, but informed speculation. It's called, the bulk is called the 5th dimension in Interstellar. And the point is that string theory, which is the best approach, the most promising approach to understanding the laws of quantum gravity, it requires that in addition to the 3 space dimensions that are so familiar to us, east, west, north, south, up, down, there also are 6 or 7 higher dimensions that are hidden from us. String theory doesn't work without those higher dimensions, but those higher dimensions are thought to be so tiny, they're sort of curled up, like taking a sheet of paper and curling it up, so it's really, really tiny. There's no way we can experience them, they're so curled up. With one exception, one of those higher dimensions could be large, and this is work by Lisa Randall and Raman Sundram a few years ago. It's speculative work, but informed speculation. It's a serious possibility. And so we rely on that in Interstellar. And so we have in Interstellar 5 dimensions, east, west, north, south, up, down, 1, 2, 3. Time is the 4th dimension, and out back, going away from our universe into the bulk, is the 5th dimension. So over and over again in the movie you hear about the fifth dimension. And the fifth dimension is described by Einstein's general relativity theory. It's so marvelous that Einstein's relativity theory that he formulated in a universe with 4 dimensions, 3 space and 1 time, it is readily carried into 5 dimensions or more dimensions and makes productions that look rather compelling. Cooper then falls into the singularity. He's caught up, scooped up by the tesseract, which is a hypercube. It's a vehicle that has 4 space dimensions. He gets caught in one face of that vehicle. The face has 3 dimensions like we're accustomed to, so he can live in the face. And then he is carried across the universe through the bulk. It lifts him out of our universe and out from inside the black hole, not by going out through the horizon, but by going up into the bulk. And he's carried back to Earth, where he docks alongside his daughter's bedroom, and then the climax of the movie occurs and the tesseract docked alongside his bedroom. You're not told this in the movie. You have to read my book about the science of Interstellar to understand that this is what. But I will tell you a little secret about how, basically how this came about. Christopher Nolan wanted Cooper to return home traveling faster than the speed of light. And I said, no, that's not going to fly. And he said, go think about it. So I went and thought about it, and I came back and said, no, it's not going to fly. And we went back and forth for 2 weeks. And then I suggested that he bring Cooper home through the bulk. And so that's what he does, though he never tells you that. That's what underlies the climax of the film. And so this then is general relativity in a speculative regime that has much of the flavor of what goes on with higher dimensional physics motivated by string theory, but it's very speculative compared to the black hole stuff, which is very firm. The wormholes in the movie are also speculation. Wormhole is named after a wormhole in an apple. If you have a wormhole in an apple and an ant, the ant has a choice of going around the surface of the apple or through the interior. The interior is like the bulk. It's a higher dimension so far as the ant is concerned. The ant's universe is this 2-dimensional surface. But he can go down the wormhole that reaches through the bulk to the other side and is a shorter trip to get to the other side. So a wormhole, similarly, if this is our universe, a wormhole would be a bridge through the bulk that leads you from this location in our universe to that location. And wormholes play a big role. A wormhole plays a big role in Interstellar. Brief history, in 1916, a guy named Ludwig Flamm in Austria discovered wormholes as a solution of Einstein's equation. 1935, this was forgotten and rediscovered by Einstein himself in 1935. But then in 1962, John Wheeler and his student Bob Fuller, using Einstein's mathematics, showed that any such wormhole will pinch off if it's empty, if there's nothing in there to hold it open. It'll pinch off and you can't go through. You'll get crushed when you try to go through, do it pinching off. And so it became obvious to me when Carl Sagan was making the movie Contact, and he needed a way to get, the book and ultimately the movie, to get Jodie Foster from here to Vega, use a wormhole. You've got to hold the wormhole open. How do you hold the wormhole open? Well, this is what I thought through and fairly easily is able to show. The only way you can do it is you've got to thread the wormhole with negative energy that will anti-gravitate. And that sounds totally ludicrous, but in fact, negative energy exists. It's made in the laboratory frequently by physicists in tiny, 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 tiny amounts. And the challenge that then I issued to my colleagues, and this is in the 1980s, is can you prove whether or not it's possible in principle to get enough negative energy inside a wormhole to repel and hold the wormhole open so that something can travel through it. And I worked on this for a while. My students worked on it a while, and a bunch of other physicists have been working on it now for a quarter century. And it looks pretty unpromising. It looks like the wormhole will always pinch off. But despite working very hard, they haven't been able to prove it. And so if I had to make a bet, I would say wormholes are probably forbidden by the laws of physics, which is rather sad. But the fact that really brilliant guys and girls, it's a mixture of men and women who worked on this, have been unable to prove, we're using the laws of physics, that wormholes always pinch off, it gives me some hope, enough hope to use a wormhole in Interstellar. So this is the wormhole, the precise shape of the wormhole that Christopher Nolan chose for Interstellar. He chose it in order to make the images of the sort that you see. The camera looks at light rays that come through the wormhole from the galaxy on the other side, and you get that is what the wormhole looks like as seen by the IMAX camera. And if you then want to travel through it, well, this is a movie made by my colleagues, collaborators at Double Negative, traveling through the wormhole. The wormhole is near Saturn. This wormhole is small, but it's very close to you. So it's gravitationally lensing Saturn, distorting the image of Saturn. Saturn's far away, so it looks like it's only a little bit bigger than the wormhole. The wormhole is just 2 kilometers in size, and Saturn is gigantic. This is a second image of Saturn caused by light rays that went around that side of the wormhole. And so you have these 2 images of Saturn like you had 2 images of a star around a black hole. So this is the trip through a wormhole. You're looking through it, you're seeing the foreign galaxy, the alien galaxy on the other side. You're plunging into the wormhole, you're nearly at the surface, you're now passing through the surface, you're now coming through out the other side, and you're now in the alien galaxy. And wasn't that exciting? So Christopher Nolan phoned me up one day. They were in the middle of editing the film. It had all been shot. He said, "We got a problem. Come over to my house and see this trip through the wormhole." So I went over and I saw, it wasn't this particular trip, but it was something equivalent. And it was not terribly exciting. I mean, to a physicist, and to you it's probably interesting, but it doesn't make for an exciting movie. And so I was going to show you the trip through the wormhole in the movie. I guess I won't show it to you for lack of time. I'll let you go back and look at the movie. Well, I guess I'll show you the beginning of it, because the beginning of it, this is all the way it really would look until they plunge into the wormhole, and then they've used artistic license. And so all of this is the way it really would look if you're in orbit around a black hole, around a wormhole with an IMAX camera. So you're just traveling around the outside of it. They're staring at the wormhole, getting their guts up to plunge in.
Goodbye to our solar system, to our galaxy. Here we go.
And now it becomes artistic license, and so in a physics lecture I won't show it to you. That's the one place in Interstellar where things were changed in a major way, just because you could not get a sufficiently exciting trip through the wormhole. It was too mundane. I'm going to conclude with some remarks about gravitational waves. This is a very exciting topic for me. It's because today, in October 2015, we're on the threshold of a revolution in our understanding of our universe as a result of gravitational wave observations. With high confidence, but not 100% confidence, I can say that we will see gravitational waves and use them to discover remarkable new things about the universe sometime between 2015 and 2019. And I'm going to conclude with a brief description of how that comes about and where this is going. Early history, 1916, Albert Einstein has formulated his equation of general relativity, his field equation. He's working with it and using it in 1916, 1 year after he formulates the equation, he predicts gravitational waves. They are ripples in the shape of space, sort of like ripples on a pond of water if you drop a rock in or stir the water with your finger. They travel, according to Einstein, at the same speed as light does because they are really tied to the structure of space and time. There's one universal speed tied to the structure of space and time. It's the speed of light and of gravitational waves. Physically, what they do is they are tidal forces, like the tidal force that raises the tides on the ocean, like by which Gargantua deforms Miller's planet. So if a gravitational wave were to go through Miller's planet from you into the screen, it would stretch Miller's planet in one direction transversely and squeeze it in the other direction, the orthogonal direction transversely. And the next half cycle, it will squeeze in the up-down direction, stretch in the horizontal direction, and it will oscillate back and forth in stretching and squeezing Miller's planet, or your instrument if you built a gravitational wave detector. 1958, Joseph Weber at the University of Maryland pioneered gravitational wave detection, but the technique that is on the verge of success is a different one, invented by Ray Weiss at MIT in 1971. And it was in 1971 that he initiated the experimental work, and it was 1971 that I initiated theoretical studies of gravitational wave sources at Caltech. Historically, what happened then was that Caltech and MIT got together. We hired a guy named Ron Drever to work on the experimental side. And in collaboration with each other, we proposed to build a gravitational wave detector called LIGO, which I will get to in just a moment. Collisions of black holes are, for me, the most interesting of the known sources of gravitational waves, so I will just talk about that for just a minute. These are the most violent events in the universe, as I will describe. This is an artist's conception of what a bulk being would see looking at two black holes that orbit around each other, merge, collide and merge and turn into one black hole. It looks fairly mundane. This was an artist's conception before we ever had numerical simulations. And this is just what the numerical simulations show, though those are in a lot more detail. But the particularly interesting thing is that the power output in gravitational waves, or the luminosity in technical terms, when two black holes collide and merge, is 10,000 times higher than the power output of all the stars in the universe put together. If the black holes are small, that power comes out very quickly, and you get out a total amount of energy, integrating up all the power, that is about a few percent of the energy or the mass of the black hole. If the black holes are gigantic like gargantua, then the collision will last for hours or days, and you still get out a few percent of the mass or the energy of the black hole. But the power, how much energy is coming out per unit time, is 10,000 universe luminosities, and that's impressive. And it's all coming out as gravitational waves, not electromagnetic waves, except that if there's a disk of hot gas, like with Gargantua, surrounding that pair of black holes, it will be disturbed by the black hole collision and shaken up enough that we expect to very likely to have some measurable large changes in how bright this accretion disk is. And so the name of the game in this field is to search for the gravitational waves with the so-called LIGO gravitational wave detector, and search with radio telescopes, optical telescopes, X-ray telescopes, gamma ray telescopes for the emission associated with a disturbed accretion disk or whatever other source is going on. The details of the collisions are encoded in the shapes of the waves. This is a shape of the wave caused by a particular pair of black holes. It's computed by supercomputer simulations, and that's actually what I've spent most of my research career on over the last decade, is putting together a research group that does these simulations so we would be able to understand the waves when we see them, and so we know what it is we're looking for. The gravity wave detectors are called gravitational wave interferometers. This is Weiss's invention with modifications by Ron Drever, who's the physicist we brought to Caltech to lead the Caltech part of the effort. You hang 4 mirrors from overhead supports. Those mirrors in the current version of LIGO weigh 40 kilograms each. And they're 4 kilometers apart. The gravitational wave, when it comes by, pushes these mirrors apart and pushes those together in the first half cycle because it's stretching along one direction and squeezing along the other. The next half cycle, it pushes these together and pushes these together, pushes those apart. And it's alternating stretching and squeezing of these the separation between the mirrors. And a technique that I won't go into called laser interferometry is used to monitor that motion. The magnitude of the motion is very impressive. This motion from two colliding black holes of the sort that we expect that we're going to see in the next few years, the motion of the mirrors is 1/10,000th the diameter, not of an atom, but of the nucleus of an atom. Incredibly small. And it's a tour de force technologically and genius technologically to have invented and built detectors capable of monitoring those kinds of motions. LIGO, the Laser Interferometer Gravitational Wave Observatory, is a collaboration of 900 scientists, 75 institutions in 14 nations. It's led currently by David Reitze, who's the director, is based at Caltech, where I am. Gabriela Gonzalez, who's at Louisiana State University, is the spokesperson. The nations involved are USA, Australia, UK, and so forth. Monash has a significant contribution to this. Duncan Galloway, Yuri Levin, Eric Thrain, and other postdocs and graduate students are working on LIGO. And so this really is a big collaboration, and it is only going to succeed because of the contributions of people from a number of institutions, including Monash. This is a photograph from the air of the interferometer at Hanford, Washington. We have a network of gravitational wave detectors of this sort. They're currently operating LIGO in Livingston, Louisiana, Hanford, Washington in the US, and in Hanover, Germany, a test instrument in Hanover, Germany that are part of the LIGO project. A separate detector in called Virgo in Pisa, Italy, that's running about 2 years behind LIGO in getting the advanced detectors up and running. And then planned for the future, one in Japan, one in India that should have been in Australia. I wish it were in Australia, but it came at a very bad time when your Australian government couldn't really see their way through to becoming the other site. And so it's India. We have to have a network for confidence that what we see is real, to extract the shapes of the gravitational waves, which is where the information is, determine the direction of the source by what I would call triangulation. I don't want to go into details. We are now working with our advanced LIGO interferometers. This is the second generation of interferometers. The first generation was basically built in order for the experimenters to get experience with these large instruments, build a simpler device as a stepping stone toward the ultimate device, and this is the ultimate device, or ultimate devices. They began their first gravitational wave search 1 month ago. So we're 1 month into that search. The sensitivity of those instruments is good enough today in this search to see colliding black holes where each black hole is 10 times heavier than the sun, out to a distance of 1 billion light years. That's 1/10 of the way to the edge of the observable universe, which is really impressive. Over the next 4 years, they will improve until they can see out to about 4 billion light years, a third of the way to the edge of the observable universe. And they're likely to see lots of colliding black holes, neutron stars, engines of gamma ray bursts, and I expect there will be some big surprises. They're likely to bring us a revolution in our understanding of the universe. It's conceivable that we will see the first gravitational waves from colliding black holes today, or tomorrow, or the next day. It's conceivable it won't come till 2017, 2019. My best guess was 2017 for the first waves, but we will see how lucky we are. The detectors are better now than I thought they would be in 2015. So I want to conclude then on that note of a very bright future, just with the remark that Einstein gave us general relativity 100 years ago. And when you look at what we have learned about warped space-time, both theoretically in terms of simulations on computers, in terms of observations and experiment, and what we expect to learn with gravitational wave detectors, when you look at how much the ideas of general relativity have been spread across the world by movies like Interstellar, I just find it truly amazing. Thank you.
What happens if you approach a naked singularity?
Okay, so I told you there are these singularities inside black holes. There's the vicious one, and there are the more gentle ones. There is a question of whether you can have singularities that are not inside black holes. We call these naked singularities. And they would be wonderful things because they're governed by the laws of quantum gravity, and we don't know those laws. And you'd be able to do experiments to study those laws, and that's what happens in Interstellar. They go inside Gargantua in order to try to do the experiment and try to learn the laws of quantum gravity. And so a naked singularity would be a wonderful thing. Most physicists believe that they can't exist. The laws of physics forbid them to exist. I have a bet with Stephen Hawking over that, and it's not resolved. But if you had a naked singularity and you went close to it, as a physicist, what I want to do is physics experiments in order to learn about the laws of quantum gravity. We don't understand what a naked singularity would be like if there are them, and so you would want to just learn about their properties as well. So they would be wonderful things for physics experiments. We probably don't have good enough technology to do those experiments yet. We don't have any naked singularities either.
You're in the running. We've got even a younger person here.
Would it be possible to destroy the universe with a black hole?
Would it be possible to destroy the universe with a black hole? So black holes are pretty small. And so if you have a black hole that weighs as much as the sun, its size is a circumference of about 20 kilometers. If you have a black hole that is as heavy as our galaxy, its size is more or less the size of our solar system, so a lot smaller than the galaxy. If you have a black hole that's as heavy as the universe, its size is the universe. So that's intriguing. But if you want to begin with the kinds of black holes that we know exist that don't get any heavier than a galaxy, they're so small that they can't really grow big enough to destroy the universe. You would have to have gigantic black holes, a lot bigger than anything we think does exist. And then, yeah, in principle, if the universe had two big enough gigantic black holes, yeah, I could imagine destroying the universe. But fortunately or unfortunately, we don't have that.
Well, we've got something even younger here, so.
Would the black hole affect the wormhole, like by bending space around the wormhole?
Yes, the black hole would affect the wormhole. So wouldn't it be interesting, since it's so hard to get out of a black hole, in Interstellar you get out by going up into the bulk, into the fifth dimension, but the fifth dimension may not exist. So let's suppose you had a wormhole, and I'll ask you, suppose you sent one mouth of the wormhole into the black hole, and you had the other mouth here. Wouldn't that be interesting?
Yeah, probably like experience something quite weird with time.
Well, there could be some things, weird things with time. You would be able to get out of the black hole by going through the wormhole. So it would take you again through the bulk into this auditorium. So you can go back and you could go from the auditorium into the interior of the black hole. And so there are technical papers written by physicists about what you could do if you had a wormhole and you put one of its mouths inside a black hole. And so, yeah, it's a wonderful combination, wormholes and black holes. But to repeat, I'm skeptical wormholes can exist, but if they can, I would sure love to have one and do things like this.
Would the Australian government fund it?
I think the Australian government has a very good record in most cases. Personally, I think a mistake was made on LIGO, but we turned to India, and India is probably 2/3 as good as a site as Australia would have been. But when you look at what Australia has done in other areas of science, and particularly in radio astronomy, it's very impressive what a nation of this size has achieved in science and technology.
Thank you, your wormhole. Well, that's the end of the DVD, so... but perhaps a few more questions.
In the visual image of Gargantua, the top ring of it was larger than the bottom. Why was that?
It was because the camera was above the equatorial plane of Gargantua, so it was closer to the top than it was to the bottom. It was just above the midplane. So if the camera had been down below the midplane, the bottom would have looked bigger.
Okay, we'll have two more questions. Maybe from the back. You choose, Eric.
When did black hole go through the wormhole and what time through it?
Yeah, so the black hole was quite interesting. The black hole will warp time at, let me start over again. Suppose you put one mouth of the wormhole inside the black hole. Then time at that mouth of the wormhole is seen from outside the mouth is slowed down enormously because of the black hole. But the wormhole leads into this auditorium, and time at the other mouth flows at the same rate. As you look through the interior of the wormhole, time is flowing at the same rate at both mouths. But when you look through the external universe, time is flowing a lot slower at the mouth that's inside the black hole. So it depends on how you do your comparison. If you compare through the external universe, time flows at very different rates. If you compare through the interior of the wormhole, it flows at the same rate. And if you think that through carefully, what are the consequences, you'll discover that enables you to take a wormhole and turn it into a time machine. Unless something intervenes. And my guess is that the wormhole self-destructs at the moment it becomes a time machine, but this is how you turn a wormhole into a time machine. So, very good question. Yeah.
Okay, question here?
So I've just been wondering, in Interstellar, when Cooper communicates with Murph through the Tesseract, because it's kind of like bootstrapping, would you say that like Cooper and the characters in Interstellar have no real free will because he can't really make the decision to do anything else but say what he said to Murph, basically?
Yeah, I'd say something like that. And this is a very interesting question. If you can have backward time travel, or we use the technical phrase closed time-like curves, this is the jargon phrase. If you can have that, then what happens with regard to going backward in time and killing your grandfather before your father was born? The standard grandfather paradox, or you can pose it in some other manner. And so Igor Novikov, a close friend and colleague of mine, Russian, some years ago gave strong arguments that the answer is that everything that occurs in the universe always has to be self-consistent. That there's no way you can possibly change history by going backward in time. And one of the strongest arguments is if it's not self-consistent, then we as physicists had better hang up our hats because we can't predict anything. But when we do analyses of in the presence of backward time travel, which I and many others have done, we, I think, essentially always assume self-consistency. We assume you have no free will in that sense. We assume that once history is writ, it can't be changed by going backward in time. But that's a deep, deep issue in physics that you can ask without putting human beings in. So we asked it in technical papers where we just played billiard balls. You send a billiard ball into a wormhole. It comes out before it went in. It hits itself and prevents itself from going in. And so then the question is, what happens? And so we convinced ourselves that, in fact, you could not change history in that way in billiard ball games. And so we begin with billiard balls, and we never managed to work our way up to human beings. Okay.
Last question.
What mystifies you most about the universe?
That's a good question.
Its existence. I mean, I would say two things. Its existence and the fact that mathematics is so extremely powerful at enabling us to understand the universe, make testable predictions about it, build the kinds of technology that we build that have made things ever so much better for the human race. I don't think it had to be that mathematics had that kind of power, but it does have. So that and the very existence of the universe, I would say. Thanks.
Now we'll just close quickly by looking at the evolution of planet Earth and 4 global cataclysms. This goes for about 2 to 3 minutes, and then we'll finish.